All right, we're set up. Talk's over. Everybody go home.
Okay.
Okay. So everyone, thanks for coming out today. We're going to talk about how to build an exchange that supports limit orders. Okay, so spot limit orders, right? And this event might be free, but by the time this thing is over, you're going to be paying me to go away and stop talking because it's going to be so much. So yeah. So does anyone know what an exchange is? Oh, and actually, before we get started, part of the reason why I'm doing this is to talk about my new thing. It's called eMeta Labs. Okay. So we're doing blockchain consulting, software consulting, and DevOps consulting, okay? And we just started, and we're doing some stuff with zero-knowledge proofs. That's all in the pipeline. If that's the kind of thing that interests you, I'd like to get your name and, talk about it with you, and we can go from there, because we've got a lot of great stuff in the pipeline. Anyway. Oh, and also, you get another free piece of pizza if you go and check out our blog. So, sear that into your eyes, so you never forget it, okay? So you try to go to sleep at night and you're like, blog.emetalabs.io, you never forget it, okay? So yeah, how to build an exchange, okay? So how to build an exchange, it supports spot limit order types, okay? So what's a limit order, okay? So you have these guys, okay, and they're basically doing this thing called an ask, okay? And an ask is like, I would like to receive this much in exchange for my good here, okay, or my service or whatever, right? And then you have these other guys called bids, okay? So these guys are akin to sellers, and this guy who's obviously under some kind of duress here, okay, because he's sweating, like someone's holding his family hostage. He really needs to get this tulip. This guy's called a bid, okay? And I've got some had to have some tulips at a fair price. No, these tulips are too expensive. I can't afford them. Yeah, story of my life. So how does this work in practice? Okay, right. So you have someone who wants to sell their tulips. Okay, they're asking for an amount, right? Like I go up to Austin here and I'm like, Austin, I would like to sell you my tulips for $12. Okay, and I have 100 of them, right? And have you guys seen Finding Nemo? Yeah, you know how they're like the birds, and they're like, mine. Well, you can think about it like these guys down here. So they're all asking, okay, they're all bidding on the right to buy this thing, okay? These tulips that this guy's trying to sell, and I'm trying to sell to Austin, okay? So, I'm selling 100 of these things, and I want to do it for $5. These guys will be like, hey, we'll pay you $6 for it instead, right? That's the way that this whole thing works, that way, right? And $5? Wait.
That's negotiator, right?
Yeah, can you say $5 to me?
$5.
Thank you. So what happens is this guy will be like, he'll look at the state of the order book, which is what this is called, okay? And he'll see everyone who's trying to sell tulips, and he'll see everyone who's trying to buy tulips, and he'll say, I'd like to sell 15 tulips for $10, and then all these little birds here that are all like, mine. They're desperately trying to get these tulips, okay? And what will happen is it looks a little bit like this, okay? So you can think about it like, like Excel, right? You have a table, okay, of the asks, okay? And then you have a table of the bids, okay? And you can see that the most expensive bid is at the top, and the asks, the very, most inexpensive one is at the bottom, and, you can sort of see what happens is that if I want to sell 10 of my tulips for $15, okay, right? What I do is I look at the order book and I say, okay, I'm going to insert my ask into the order book by finding whatever, like let's say I'm asking for an amount. I find anybody who's willing to pay more than that amount already, okay? And then I take the amount off their hands, okay? And it reduces the amount that I'm looking to, to sell. So in this case, I start out with 15, okay? And I want to sell it for $5, okay? Someone else is already willing to buy this much for $5, okay? But they're only selling 10 of it, okay? So the amount gets reduced by 10, okay? Until we have 5 left over, right? And you can see that here. And then what happens is that after this happens, only 10 was fulfilled, or filled is what they call it, by the way, then gets thrown in, and it gets added into the order book on the side of the asks, okay? So what was originally 15, right, at a price of $5, 10 of it was filled by the very number one order on the bids, okay? And who's messaging me right now? All right, I'm just going to put my phone on Do Not Disturb, okay? Just 'cause... Okay, jeez. You can see there's only 5 left over at a price of $5, okay? So how is this represented in code? Because I just showed you how to do this in Excel, okay, right? And you might say, this is pretty easy, we're going to use an array, okay? And you could, right? But that's a very large memory allocation, okay? So they're trying to bring this into the realm of the programmers here, because you have to allocate for every price point, or you have to have some way of sort of like inserting things and segmenting them, right? So in this example, well, the example I'm going to, talk about with you guys today is we're using a pair of AVL trees, okay? So does anyone know what an AVL tree is?
Binary tree, AVL.
So
Alright, guys.
This guy knows.
Well, it's the one that like rotates to balance, right?
Yeah, exactly right. It's a self-balancing binary tree, okay? Right? So let's say we have the order book, and it's just like what I showed you before. Well, it's not quite just like it, but it's very similar, okay? This is how to be represented on the asks side, and this is how to be represented on the bids side, okay? So this data structure always sort of ensures that things are in balance, sort of like this. See how the middle bit there? And there's never like a long line that goes down. It's always just like that. It's kind of flat, right? So let's say that I wanted to, make an ask. Okay, I wanted to offload 45 of my tulips. So we're right in the prime of this, that tulip crash or whatever that happened before. I thought it'd be funny to say this. On turnips. Does anyone know what turnips are?
This is a very special tulip.
That's exactly right. Yeah. This guy's made a lot of money. So we have 45 of these asks, okay? And they're priced at $3, okay? So this is what happens when we go to make an insertion into our AVL tree. What happens is first of all, if they're basically, this is like when you're in a movie theater and the phone picks up and it's like... So what happens is that the bids, first of all, because this is at a price of $3, okay? It takes the $3 bids here, okay? Takes the $2 bids here, okay? And wait a minute. Yeah. Did I do this the right way around? We're just going to roll with it. So what will happen is it'll take part of the bid side, okay? And then it will insert asks into the other side, and it will balance the tree, okay? So what was originally like this, which is $12 and then $8 on the left side, $15 on the other side, it makes an insertion, okay? And then it rebalances the tree, okay? Now, the reason why you'd use an AVL tree as opposed to using like an array or like a hash table or something where you have constant time access and constant time lookup is because of, like I was saying before, it's a very large allocation, right? And this very large allocation is basically like, you have to take, people call this an arena, okay? Where you allocate a lot, and I'm looking at David for confirmation here. You allocate a very large block of memory, okay? And then you put things in, and you know where the offsets are, and it's like having a very large array, basically. That's what it is, right? This is sort of doing something, it's not similar, but you're sort of offloading all of the responsibility of knowing how to allocate where the memory is located to this very sparse data structure, okay, which is this AVL tree, right? So this isn't very performant, relatively speaking, to the way that you might use an array, okay? But this is a lot easier to allocate and a lot easier to work with, and I also think it's a little bit easier conceptually, which is why we're talking about it today. So this is how it might look in code, okay? And I wrote this in OCaml. This is just an example. Hell, I even wrote a bit of code to actually show off how to actually do the actual insertions, but I don't have that here today. So I'm going to break it down, okay? So, hey, Pasha. Did you make it in time? So here we have a type, okay, called a position, okay? And this is like when you have like in Java, when you identify what the type of the key is, and then you identify what the value should be. That's what this bit here is, okay? It has the price, and by the way, you're going to pick up on the fact that there are no floating points in this example. People don't trade with floating points. I mean, who am I kidding? So we've got a price, and then we've got a first in, first out queue, okay, that I've just called a FIFO here, okay, that contains types of order ID, okay, and an order ID in this case is just like, it could be like a string to refer to like an item in a map, like going back in time a little bit. Oh, yeah, here we go. So I said map there, right? This is a purely functional approach. So I've skimmed out a little bit on some of the explaining here, but you basically have a map that would contain everybody's orders, okay, that you can sort of do a lookup into, okay, and this could be a hash table, this could be just like in a map that's another binary, like another balancing tree, like a binary tree, for example, right? And what you sort of do is you basically say this is a first in, first out queue, and then you store that on the AVL tree, right? And this is what the first in, first out queue looks like, and this is code that I'm going to skim over in 5 seconds because nobody wants to read this. So this is just a functional way of doing like a FIFO when you have two lists, okay? And you have one side which you keep prepending, excuse me. You keep prepending to the one side, okay? You keep throwing stuff at it, and that's the back of the FIFO queue, okay? And then when someone wants to get something from the front, you do a reversal, and you just reverse everything, and then you start popping off of this reverse list, right, which is the front side. So back, front, but I don't expect anybody to read OCaml, so I'm just going to keep moving. So yeah, we have a type here, okay, that's a record, all right, and it contains the smallest, okay, amount in one of these, these trees, and then it contains the highest amount, okay? And then it contains a tree, and this is just for fast lookup in this example, okay? And then we have two types to distinguish what the order books should look like for two different things, and that's just type level programming, right? So how do you fill a position with this AVL tree? Okay, so just going back in time a little bit here. You've got, this tree. How do I actually fill so you can have changes that happen like with what happened here, right? So the steps you take are like this. First of all, you go to the other side of the order map, okay? And if you're making an ask, you go to the top side, okay? And you get all the smallest order on one side. But by the way, this is after checking the record we showed before to say what's the smallest versus what's the highest. And you got all the smaller orders on one side, okay? And then you go through everything recursively and all of the FIFOs, okay? You know how we showed off the FIFOs a minute ago? You go through everything with an amount that you have until, you fill it or you run out, right? And if you run out, then you create a position on the other side, okay? And I've got a diagram to show this off because Shamir's looking a little bit confused here. So, this is this is what it looks like, okay? So we start off and we create a bid, okay? And we say, are there any asks smaller than the current order, right? And if it's no, then you create a new bid position or you append, an amount order ID to an existing position for the amount that you asked for, okay? Excuse me, that might have been a mistake there. But if you have got asks that are smaller than the current order, right? What you do is you begin to reduce the smaller asks, okay? And that's going through everything, and you're like, does this say text? Oh no, it does. You start reducing the smaller asks, okay? And then if there are any amounts left over, right? What you do is you create a new position with the order ID, and you create a new FIFO queue, okay? And if not, then your order is drained, and everyone gets to go home happy, right? So this is a very self-contained loop about how to do order filling, okay? But how do you communicate this to somebody, all right, who has got a position in the order book and they want to know if their order's been liquidated, okay? So, and this is how we keep things on topic with functional programming, because everybody in the room who has some familiarity with concurrency is going to say, oh man, this guy should have just used concurrency instead. Well, you're right. And the appearance is the same, and you'll understand what I mean in a sec, right? So what is functional reactive programming? Has anyone used React before? I think everybody should put their hands up. I mean, I'm not going to... Rob's has to put his hand up. Yeah, well, you're right about that, okay? So it's where you have a system where you have sort of like, in some cases, a closed event loop, okay? And you have purely asynchronous reactive code, okay? So that when something happens, you pull in that event, okay? And you indicate that that's happened, right? And then you kick off some code that updates the state. It's sort of a bit like having if anyone's ever written Erlang before, you have your loop and then you received a message and that's, you handle it, right? But you have two types. You have events, okay? And events occur discretely, so they can be generated by a side effect or like a timer that kicks that off. And then you have a signal, okay, that produces a value every time, it's accessed, right? And then this is just some code on the right that shows off how you might be able to do that. And, that's using the OCaml React code base, right? So you can implement an order book like you would with a concurrent system, except using, has anyone ever used Kafka before? Nobody's used Kafka, okay, that's a shame. Well, or like a message broker, and then you have like a topic, and you can filter on the topic, right? You sort of take code and you sort of like do a fold on it, and you do like a reduce on it. So you can do things where you take in these events that are coming in, and then you can sort of transform them and spit out another bit of events that just like keep happening, and you keep processing, and it's all asynchronous, right? So how does this actually work in terms of like technical architecture? Okay, because you've got all this up, and that's like a little closed little environment. Okay, it lives inside of your runtime or whatever. It just does its thing, right? So this is how it looks with signals. Okay. So first of all, the hand knows the state of the order book. Okay, and that's by absorbing every event, probably, right? And the hand decides it wants to make an ask. Okay. So what happens is that the hand makes an order, okay? So like I say, it says, I want to sell 45 tulips for $12, okay? This is my ask, okay? And it relays that information down as a signal, okay? And then you have a bit of code that's reacting to events being passed down the thing, right? With its own little order book that it keeps in mind, okay? And what happens is that it will sort of indicate a field or like an order creation, okay? Right? But this is interesting because, in terms of actual technical infrastructure, you can support all of this using like a message broker, which is like a fan-out message queue, okay? Right? So answer, Mosquito. If anyone's ever used Mosquito or Rabbit before, where you have like an event and then you react to that and it gets pushed out to everybody. So like if I'm in the room and I yell, fire, right? Like everybody in this room is going to get that information, okay? Because of the way that a fan-out message bus works, right? So this is just an example of what I just said. You have your Mosquito code and you do a publish to a topic, okay? And a topic is a way of identifying something, okay? And you have your message, right? And then you have a subscription, right? And it takes a topic and it will, every time it receives a message, it will relay that information out. And that goes to both of these clients, okay? So this is how you might actually architect this thing in terms of like event queues and, message buses or whatever, right? So this is with like a trusted sort of approach to topics, okay? We have a client that decides it wants to make a notification, okay? And it wants to make an order, okay? And it has a state of the order book, okay? So what it does is it relays a message down its very special topic that nobody else knows about, so nobody else can get that information from, okay? And it's a fan-out message bus, okay? We'll show it a whiteboard. So it's like if I said to Ivan, it's like, Ivan, come here. We're doing this. This is a live demo. This is a live demo. Okay, so I whisper in Ivan's ear, Snape kills Dumbledore. You don't know.
Oh no, bro! Spoilers, man.
I didn't watch Harry Potter. I just know that for some reason. So nobody else in the room presumably would have picked up on that information. Okay, right. So I do that, and I tell Ivan that Snape kills Dumbledore. And in this case, I say I would like to sell 10 of my tulips. Okay. And Ivan has an idea of about how many tulips I have in my possession, okay? And then Ivan looks at that and he says, all right, everybody, you know what? This guy does actually have the tulips he wants to sell, okay? This guy is not JP Morgan. He's not trying to short sell silver. And what happens is that he will do like an update to the balances database after, checking it, okay? And then he will relay that information to the order book server, okay? And this gets relayed down a topic, which is order book update, that everybody gets a copy of, okay? So Shamir's listening in, okay? Shamir knows that I'm selling my tulips, okay? 12, right? $40. And so he has a copy of his own order book that he updates, okay? Accordingly, right? Because he's just found out that I'm selling my tulips. He's like, I'm going to be the other side of that equation. I'm going to sell. I'm going to buy. I'm going to be the buyer. So he swings in, But what will also happen is that the order book server will relay a message down to every client, okay? But what it will also do is you have this thing called an order book relayer, okay? And the order book relayer, right, has a copy of every transaction that's ever come through, and it's got its own copy of the order book, okay? So that when a client goes to connect, it sends it a copy of its own internal order book for everybody to get a copy of, okay? So let's say, I have 10 tulips and I'm selling them for $5. I have 20 tulips and I'm selling them for $5. I'm desperate, right? And we're right at the end of the crash, okay? So, I know this information. Shamir is the designated relayer, okay? So, if anybody comes in and they want to make a transaction of their own, right, they will get a copy from Shamir of the state of the order book, okay? So, this information will get relayed to the client, okay? Down the topic here, right? Oh, balances up there. Yeah, and that's actually how it works. So that's how it goes in terms of say somebody goes in to make an order, then they broadcast information to everybody, and if somebody gets filled, everyone will already know. But anyway, this will tell everybody, right? You know, the whole thing here is that you can actually write code that internally appears like functional reactive programming, but on the outside, the infrastructure level is message bus driven, okay? And you know, this is like when you're writing JavaScript and you're in callback hell, okay? And you're processing, you've got like 15 layers of like depth, you know, just like, it's like the Mariana Trench, of just like of callbacks that you're in, right? I guess that is a kind of functional reactive programming, okay? So relating it to the diagram of what I showed you before, okay? So the hand has decided it wants to get, it's got a copy of the order book from the order book relayer by the same topic as everybody else. The hand decides it wants to make an ask, okay, so it goes here. Then what happens is that the order middleware here, okay, well actually this just translates it out, excuse me. The order book server checks in with the balance of the system and it checks if the hand has enough money to make an ask to actually sell this thing, you know, says do you have enough tulips, you have 12 tulips to sell, right? And it will check that, and if it does, it will relay that information down the order book update server, okay? Right? The order book update server will even, through the order book relayer here, okay, notify all of the attached clients that any fields were created and that the order's been created, and it will update its own internal order book, okay? So it's kind of like this little cycle here of like selling and then, you know, balance is getting updated. Anyway, everybody, you know, that was it. That was my portion. Now I'm going to hand you over to the more...
Prior to finalizing your portion, do you want to sort of like summarize when it comes to the actual utility of using like functional programming in this, as well as, you know, comparing with, you know, existing markets?
Well, functional programming relative to like imperative style programming, you know, where you're doing a lot of mutations and you're changing a lot of things, is that it's very easy to distribute, okay? So you can have like a system where you've got like all these different little bits here. And, you know, these bits are very disparate, okay? They're not on one big thing, right? They could be running anywhere. They're all getting their information via the queue. And inside of them, they could be even more little, like, broken up and disparate and, you know, like split up and all these different things, okay? Relative to, like, imperative programming where you might have, like, not that you can't use a mix, right? Because, you know, if you wanted to, what you could do is you could, like... We talked about using AVL trees for this, okay? But how do I go back in time to a long while? Oh, God. So we used AVL trees here, okay? So in summary, we used AVL trees, 2 AVL trees for the asks and for the bids, okay? Sparse data structures, okay? They're not very cache friendly, okay? You know, you're not going to be storing this information and doing a very fast lookup of it. This is going to happen in logarithmic time, okay? So, relatively speaking to using like an array, for example, is that can be very easy to implement. It's very easy to reason about. And the best part is that in your standard library for whatever programming language you use, it ships with an AVL tree. And if it doesn't, you can always just use the map type that I'm sure it comes with, right? As opposed to a multi-dimensional array made up of linked lists or something similar, right? Which is the point where, you know, you're just like, that. But, yeah.
Is that because of the efficiency that you'd say?
Yeah, it's more efficient to use like a array, obviously, because, you know, like you can do vector operations on, you know, the structure that's stored there, and, you know, it's cache friendly. Because with this, you're basically outsourcing the memory allocation work to, you know, to your allocator, right? That's obvious, okay? But the downside is that, you know, it's not as cache friendly because this could be stored in the middle of nowhere. You know, it's disparate in structure, right? So going forward in time. So the advantages to using this approach compared to, well, actually, you know, I kind of think of it, I don't actually know another approach to do this. This is the only way I do it. Not necessarily the function reactive programming, but this structure, okay? So I give you a good reason, but, you know, you'd have to really, you'd have to show me the alternatives. Anyway, I hope you guys enjoyed that whirlwind of a technical tour, okay? You know, if you could take some photos of the zoo animals on the way out, you know, if you want to.
You can take some questions on that side before you go to
Yeah, that's a good idea. Okay, so does anybody want to know anything that I can help you with? Jasper.
So, if there's a bid that's asking for a higher price than the current sells, will the exchange just pocket the difference, or what will happen?
Well, wait, did you say bid? Excuse me?
So if someone wants to buy for more than they're offering,
Yeah.
will the exchange pocket?
Well, what will happen is that everybody who's within, like, underneath, I mean, everybody who's, you know, who's underneath the amount. So, like, let's say you're selling it for you want to buy it for $12, you know, Ivan is selling it for $9, I'm selling it for $10, right? What will happen is that we will fill your order, okay, so that you will get in at a cheaper amount, okay? So like let's say I'm selling 10 of it, Ivan's selling 20 of it, but you want to buy 40, right? Then the remaining $10 will be created as a separate, you know, as a separate side of, you said bid, right? Yeah, it was a bid. Gets created as a separate side for someone else to come in and try to get that later on. Does that make sense?
Yep.
Cool. So, anybody know anything before we get into the fun talk, which is the Solidity Ethereum? Ivan?
Sure. I don't have any questions.
You don't have any questions? Okay. Sure. You want to know how to relate this to a DEX? I can't help you. All right. We were going to do a break before, but I think we, you know, since we started it late, you want to get started?
Yeah, let's do it.
All right. Now everybody gets to watch a pro give a talk.
Bro. All right.
Yeah.
All right. So the first part of the talk was really like the most interesting part, I think, which is the more niche type as well, just talking about actually building an exchange and actually how it more so works. This is just going to be a little overview about Solidity, which is the programming language utilized within Ethereum as well as its components such as EVMs, and just like a bit of an overall of components within Ethereum, because I know that there's, you know, there's a mixed crowd. Some people know a lot, some people don't know a lot, and some people, you know, they don't know what Solidity is. So first of all, what is Ethereum? So Ethereum is essentially a distributed ledger, much like Bitcoin, but in this, instead of just being for transaction's sake, it's really primarily, it can be used for anything, right? It's anything. It can be used for distributed computation, where you're able to forward some sort of transaction and have it be computed by someone else, right? You can pretty much, it's like cloud computing in that sense, but the cloud computing is happening in other people's computers and they're getting rewarded for it. So it's the mining process. So the idea of Ethereum also involves the EVM, which is what does the processing, so much like the JVM, if you're familiar with Java and JavaScript, that pretty much does the conversion as well as the execution from higher level code to bytecode. So, you know, miners are incentivized to actually be able to perform the operations that would result in the smart contracts to be executed. The smart contracts being the, let's just say, the packets that are sent within the blocks of the blockchain. We'll get more into that later on. And that's amazing, that's great, you know, but much like utilizing a distributed system, there are some caveats to it. And the caveat with Ethereum, at least right now, is it's really, really computationally expensive, like tremendously. This is like Bitcoin. Hey, what's
How
up?
much does it cost to use Uniswap? $70.
Too much. Yeah, I tried to make an exchange the other day, and it's like $70 to
I should have lost more on that.
Yeah, crazy. So because of that, there are lots of solutions that people have been trying to get live since its inception, really. So I think Ethereum launched its mainnet in 2014, I believe. And since 2015, 2016, people have been trying to do layer 2 solutions or sharding or state channels or side channels. So I put a little question mark there because these slides are a bit old, but at the time when these slides were relevant, when I made them, Casper and Plasma, they were the two big solutions that would change everything. But, you know, it's 5 years later. We're still waiting for Casper and Plasma.
So you've been in a coma, it's been 10 years.
Yeah, so what Casper essentially do is instead of being the proof of work mechanism, which just like Bitcoin operates in, which is the hash rate, so it pretty much uses the computational power of your computer in order to execute on the blocks and on the actual transactions for the confirmation of blocks. The way that Casper would do is you essentially create a proof of stake system where you actually stake, like you essentially bid in your money, right? You bundle up your money and the execution works almost like a lottery type of system. And Plasma, the way that it works is, if I believe it's like a state channel, I think, which is just like micro channels that then aggregate into a bigger one, and then it's pretty much child chains from the big blockchain, and then it sort of aggregates those answers and send them to the main chain slowly, so it conserves a lot of the costs there. So since the inception of blockchain, or since the inception of Ethereum in this case, we've had layer 1, which is the first layer of the blockchain, you know, the way that it works. So block 1, block 2, block 3, much like Alex explained, it's almost like a linked list, right? It's a linked list of blocks with data inside of it, so it's not just addresses in this case. but people have been working on layer 2 solutions. Some of the layer 2 solutions that we explored before with the Solidity, within Ethereum were Plasma and Casper, but there's some other layer 2 solutions which are, instead of just creating Ethereum 2.0, for example, they are actually trying to scale on top of the original existing solution. And one of them is Optimistic Ethereum. Yeah, what's up?
Did they mean it to look like the dark side of the moon?
Yeah.
You know, the album?
Yeah. So one of them is Optimistic Ethereum, which is actually already out. So you can actually use Optimistic Ethereum, and it's pretty damn fast, but it's not great. Another one which I'm a big fan of is what's it called? Off-Chain Labs Arbitrum, right? So it's a big R over here, Arbitrum, which essentially uses Chainlink, right, as for off-chain computation. So you essentially have so these two solutions are very similar in the sense that they want to try and off-put all the calculation, all the computation from being done on-chain to being done off-chain. And then what they do is they get the data that's produced and then they compress it and put it back onto the blockchain. So right now, the reason why transactions are so slow is because you have like a bottleneck when it comes to the actual throughput of transactions. So these guys, what they're trying to do is they're trying to have a secure way to do it off-chain. And one of these uses Chainlink. And me being a big Chainlink advocate, I think that they're doing a good job.
So it's Chainlink and Oracle.
That's right. Yes, so Chainlink is an Oracle distributed or Oracle network. Yeah. We can get more and talk about that later on. So just prior to that, I just wanted to show an example of what Solidity code looks like. Right. So Solidity is statically typed. It's a programming language. That's the programming language that's used in Ethereum, and it's very, very similar to C++, C# or Java. Like it's inspired that way. It's very spaghetti code, like the way that. If you actually, so the cool thing about Ethereum and blockchain stuff is that all the code is available on chain. So if you want, you can literally just click on a code on Etherscan or something like that, and you can actually see the source code, and you'll see that a lot of it's not well written. But
Yeah, actually, come to think of it, we're dealing with an Ethereum bug right now, aren't we?
yeah, the get bug. That's right.
I'm
Yeah.
gonna have to make an actual issue.
So what are smart contracts, right? So we're talking about Ethereum. We'll talk about how cool it is to have your transactions being executed elsewhere in the cloud, and whoa, I just pay money and someone gives me the answers, right? It's like slavery with less steps, right? So the cool thing about smart contracts, or just in general smart contracts that they're self-executing contracts based upon specific conditions. So you have a condition such as, whenever Ethereum reaches X amount of price, sell whatever ICO coin that you bought for, a lot less than you're currently selling it for, right? So like, originally, the idea of this is to create a world computer. So instead of just create, much like Bitcoin at the time, you could make transactions. So you could send transactions to one person, another person. So the financial system was, oh my God, we have to ban Bitcoin and all sort of stuff. Right now, there's the idea of Ethereum is that they're doing that with logic. So you're actually able to execute on that type of stuff. Oracles come in later on, and I think that that's a big part of this actual scalability of smart contracts. To actually be able to execute on real-world data securely, but that's something for later on anyway. So smart contracts have a lot of applications. I think someone earlier on was talking about smart contracts and IoT applications, which was quite nice to see because yes, you are able to use smart contracts with IoT applications. It sucks that I'm not streaming from the computer; it's from the phone. But trust me, this guy types a few numbers, the doorbell rings, he sends a transaction with his wallet, Alpha Wallet, whatever it is. And then the door unlocks. The door is unlocked, right? So it's, what's up?
How long ago was the video made?
2018, August, September.
I was going to say, was this guy like a millionaire? It's something like that.
But yeah, like you are able to use smart contracts for more than just trading your tokens online. Like there is a lot of utility to it, whether it is for weather data on executing insurance claims, whether it is on actually being able to buy and sell tokens, whether it is on actually being able to provide for logic for, if the car has been parked here for X amount of time, and then you sort of like send a transaction of the amount of time that it's been from that car. So I'm trying to like allude to smart parking. And then it sends a transaction directly to your wallet, which you sort of like pay. So instead of you having to go pay out whenever you back out of your drive-through or the place that you've been parked on, you have a transaction, and then you just accept it, and bang, that's smart park, right? It's pretty cool. So within Ethereum, the way that it works and why people are incentivized to use it in the first place, much like Bitcoin, they have rewards called no, in Ethereum's case, it's called Ether, and Ether is an ERC20 token. So ERC is just a standard of tokens. So ERC20 tokens are fungible tokens. So they are tokens that are sort of one-to-one, much like currency. So you're able to exchange them very easily, and they're compliant to whatever you want. Like you can buy things with it. You can use it for gas fees in Ethereum, which is what you pay the miners. You can use it to exchange money. You can use it to execute transactions. You can use it for all those type of things. But the cool thing about Ethereum is that you're able to create different standards of tokens, right? And that's where you have the ERC 721 standards, which is the non-fungible tokens NFTs, which I'm sure everyone's heard of. You have the CryptoKitties, you have the hash masks, which is one of the latest ones. It's art on the blockchain.
Wow.
Yeah, it's really cool stuff. If you got one of these early on, you'd be a gorillionaire right now. And there's a Top Shot, which I think Alex mentioned earlier on, where NBA has these collectible
Like
cards.
actual NBA plays, you can own a play.
Yeah.
Like if someone when
No,
Charlie
it's
shoots
not actual
ball
players
through
though, man. It's just the
the
card.
play, no the play.
The play.
The play.
Ooh.
Like when this guy scores a good goal, it's like, oh, that was a good shot.
Yeah.
That's on flow. No.
That's on flow.
Is that on Flow?
Are you serious? Wow. Okay. Well, there you go.
There is 250 million for that.
Yeah, I heard about that.
Yeah.
That's what I was paying attention to. I didn't even look it up.
So one of the cool stuff, like I said, the slides are a bit older, so we're talking about primarily CryptoKitties right now. But at the time, whenever NFTs were created, whenever CryptoKitties was the big hype, they sold one CryptoKitty that one of the Genesis, as in like the original CryptoKitties that were generated, because there's various generations. And the cool thing about NFTs, non-fungible, just means that they aren't one-to-one. They have differences. Like every single token is unique, because every single token's unique hash has like unique properties that generate, really cool stuff. So, and really cool stuff just means that they aren't the same. And one of the kitties that were sold for like over $117,000. So it's wow, yeah, crazy. So literally bytes that someone just bought and sold for like that amount of money.
Cat.
Very expensive cat.
The ancient Egypt of the internet.
Precisely. And then you have DEXs, which are decentralized exchanges, and they operate quite similar to the exchanges that Alex was talking about earlier, but the difference is that they are unregulated. So what that means is that there is no central entity that actually governs if you are able to transact in it or not. For example, there are Coinbase, I think, they don't allow X token to be sold there, and that's because they have to operate within the United States, and within the United States they can't sell this token because it's a regulated security. Yo, what's up?
So things as the miners are the ones who are mining blocks, and they can basically say that this transaction shouldn't be random if it's using Uniswap, for example. Do you think that someday they'll refuse to add a transaction? I mean, to a block if it involves Uniswap?
I don't think that they would actually do that, and that's just because the incentive for the people that provide liquidity is just to keep the system running, because they actually earn money over it. Yeah. So the way that it works is through provision of liquidity. So there are people that provide liquidity, and what that means is that they provide a one-to-one. Let's just say you can have a liquidity pool where people are able to put in, and by people I mean like Alex, for example. They put, let's say it's a 50-50 liquidity pool for one ETH to USD, right? So one ETH, let's say, is 2,200 USD, right? So that means that Alex, for every Ethereum that Alex puts into the liquidity pool, Alex has to put an equivalent of 2,200 USD, and then he gets rewarded. So he's pretty much providing liquidity for that trading pool, and he's rewarded with the transaction, like let's say 0.3% of the transaction fees.
Liquidity in this case is just like you pay somebody in a traditional way to do a market making job, which means that their job is just to be involved in that market. Their job is to trade. Like Shamir, like they just go and they're like, we want you to trade all day, do 10 trades a minute or something, right? That's market making.
Yeah. But
Right, just keep it stable. Actually.
no, it's less about them making trades, and it's more about them providing liquidity to the market, right? So liquidity pools, and one of the big things that comes with liquidity pools are yield farming, right? So I think yield farming is on the next slide. Yeah, so yield farming is so crazy stuff. So imagine getting this much APY on like your bank account, right? Crazy. That's how they trap you. And then like 2 days later, whenever the pool's dried up, they go like, 1,000%. I meant 0.01% per annum. Yeah. So that's pretty much what I explained earlier on. People provide money within the market, so people can do trades because it's a decentralized market, and they get rewarded for putting this money in. So they're essentially farming rewards. So they're putting their hard-earned money and collecting the fees, if you will. But it's not that easy. There is a lot of I think there's something called impermanent loss, where if the price of something goes up and they keep their money there and actually retrieve it, they actually lose money. But it's called impermanent because if you leave it there long enough, you hope that the market stabilizes and you can cash out. So and you can you hope the fees actually even out with the amount of money that you lose. But that's a different conversation. But all of these things that I'm talking about right now, what they are part of is this movement that started about 1 or 2 years ago. So much like the ICOs, which are initial coin offerings of 2017, there started being something called DeFi, which is decentralized finance, where people started building these applications which are really cool. You can lend money, you can borrow money, you can it's a lot to do with money, but you can do a lot to do with money as well. It's like yield farm. You can provide you can become a node operator for a network to secure the network, and you actually earn money out of this. So it's almost like the financial system's equivalents, but in a very easy to do way. So for example, I have a friend called Thomas Hodges, right? And Thomas, he wanted to borrow money from the bank, and he wanted to borrow, let's say, like $10,000, and he puts like the collateral of like whatever one-to-one collateral, whatever it is. The amount of paperwork that he would have to go through is like crazy. Like it's just to borrow that amount of money, just like, oh, maybe you have a high credit score, but you don't live in the United States, or but there was this one time that you did this, and you have to have your bank history checked, and 2 weeks later you're still waiting. Or you could go to Aave, which is a lending protocol, and you could literally just put in money and borrow money in like 5 minutes. Like it's crazy. It's like it really challenges the current financial system, right? And this stuff is happening like today, right now. So what is it going back? Yeah, it's going back. So that's what DeFi is, really.
Badge it down. Okay.
So these beautiful slides right now were sponsored by Shamir, and there's this thing called wrapped Ethereum tokens, right? And what wrapped Ethereum tokens are is you're essentially able to obtain a token from another blockchain. You send it to like a ledger, not a ledger, like an escrow that holds these tokens, like in a specific place, and then new tokens are minted, which are the Ethereum equivalent of those tokens. So the escrow is really secure, so you know that those exact number of tokens are there. But what this allows you to do is you can expand the amount of applications that you're able to utilize within Ethereum specifically. Like you're able to wrap these tokens and then use them in a different blockchain. So pretty cool stuff.
You gotta wrap them up like a mummy.
Yeah, that's it. Yeah.
The ancient Egypt thing.
Yeah. So smart contracts, the way that they execute really is much like in a computer. You have your program executes. This is like your local environment computer executes, but the way that I do is you execute them, you send it to the blockchain, and there's multiple millions of copies of them. People are able to audit them and exploit them if they want. But the idea is that everything is online. Everything is able to be seen. Everything is able to be explored. Everything is transparent, right? And that's a really good thing about the blockchain as well, and a bad thing about the blockchain. You're able to actually verify your contracts and actually see their code, their source code, as well as the bytecode that composes of them in services like Etherscan. So you actually have the contract address over here. So this is like a regular contract address, usually starts with 0x, and then this really long sort of digit code that's like the hash of the actual contract itself, or the transaction, if you will. And here's like the bytecode that composes of it. So this is just this is the ABI, and what it does is it's the something interface. Yeah, that's right. Application binary interface. That's right. And what it does is it converts that high-level code into something that the EVM is actually able to execute. Yeah. So you're able to see all this type of stuff, right? And you're actually able to verify and see. You're actually able to verify and see if someone's the owner of a contract, for example, for them to be able to execute on functions. And if you have let's say a lot or an election that's on the blockchain, right? One of the good things, or one of the bad things in this case, depending on how you actually make them, if you're using like a ZK snark, like zero knowledge proof, you are able to say that you voted on it without showing that you voted on it. But if we're just using Ethereum as like a basis for it, you can have a ballot on a blockchain, and you're able to, if I knew what Alex used as his address, his wallet address, in order to vote, I would be able to see who he voted for and when he executed this, because he's making a write transaction on the blockchain. Every time you write on the blockchain, you write on a new block, but you can read on the blockchain from the blockchain as many times as you want without spending money.
Yeah.
Yeah.
The addresses are pseudo-anonymous, so that you don't necessarily know who, but once you've tracked, you will know. You can track everything that they do and every interaction.
That's right. Yeah. So that's a good point Alex brings. So a lot of people are talking about Bitcoin and how it's anonymous and all this sort of stuff. It's not really anonymous at all. It's if you know one address, you can do myriads of attacks, to try and decode who this address belongs to, type of thing. But they are anonymous to the sense that they don't have a username to them, or they don't have a right now. If I told you that this is Alex's username, right? You'd be like, oh shit, I couldn't tell. I wouldn't be able to tell. But yeah.
I got a cool username.
Very cool username. Yeah, very cool username. So your data is public. So once again, as I said, everything that you publish on the blockchain is public, and it's publicly able to be accessible. You are able to call public functions as well. So much like your regular programming language, there are, I think, the modifiers, I think that's what they call it. So you have your private, public, and all that sort of stuff. And if a function is public, then anyone's able to call it. So don't make if you're making your own currency, don't make a mint function and put it public,
Well, I'm trying to tell that to some of the DeFi guys, I'm sure.
Yeah. a few of the DeFi guys, the YAM guys, and the vulnerability. Yeah. So, as I said, be careful what type of functions you include there, because if you have a malicious function .exe instead of anyone's able to execute it, and functions are public by default. So.
Yeah, if you just tap it as well, by the way.
Did you tap it? Yeah.
If you just tap it, it'll just
So one of the big hacks that happens. So there are multiple hacks, but two of the big hacks that I see mentioned multiple times, even when I was in this other talk, just the last week, and they go the DAO hack. You guys remember that? That's why you can't do autonomous organizations on the blockchain. I'm like, God, that's so old. There are so many governance platforms right now.
Yeah, there's even a video. You know that guy who's I don't know which country. Is it from Spain? He's laughing. He's like that. The one where it's an iPhone or something, and he starts laughing, and it's what the, you know what I mean?
No, I don't.
There's a version of that, and you have the video and the guy, and he's laughing, and he's just the DAO, the slot guys, the slot guys, Sounds on news.
I had a chat with the professor at Adelaide University the other day, and he's just see, can't do this type of stuff because the DAO hack, and I'm that was just re-entrancy. That was just a mishap on the actual programmer side of things rather than the actual blockchain's issue itself. There are hacks that do occur in the blockchain, but a lot of them is so unlike regular cybersecurity, where it's more let me try and penetrate the system in order to try and socially engineer this person to do this person. Although you can socially engineer someone for their private address and all that
they
stuff.
call that doing the crowbar.
The crowbar.
You have a crowbar, and you're I'll get your knee with this thing. Yeah.
Very morbid. Yeah, I like that. Yeah, but the way that you usually see hacks happen in the blockchain is that someone just didn't think about a specific way that people would execute on this function. Just because the functions are publicly accessible, if there is any sort of mathematical mishap, or someone did not account for a certain way that you could utilize this function, or a callback function, so you have another smart contract that then is loaded with lots of other contracts, so it's almost like a DDoS, and then they are able to attack this certain smart contract and overload it, for example, or make some sort of buffer overflow in it. You can potentially lose all your money. So that's why smart contract auditing is such a big business. It's a huge business, big business. So yeah, implicit visibility, I sort of already spoke about that. And you just have to be careful not to, whenever you're creating a smart contract. The reason I showed a smart contract earlier on is just to sort of demystify, and that's what I want to get into later on. I just want to demystify how hard it is for you to actually get into Solidity. It's not hard at all. It's literally just another programming language. It's just because it's very niche, and someone says, "Oh, I'm a smart contract developer," and you feel very oh my God, smart contract. Wow, that's great. I just know Java.
You feel very intimidated. You're like, oh, this guy.
Yeah.
Oh, this guy.
But so I was just gonna go through some vulnerabilities over here, such as integer overflow and underflow, and you're able to have some sort of like attack where you can go over the amount of specified integer overflow and underflow. Really.
Do you think it's more of a like a problem with a programming language and more a problem with the bytecode interpreter that it's possible to do integer on the fly?
I think it might be I'm not sure if it's a bytecode interpreter. It might be like foresight. Is that the right word on the actual programming language itself? So a lot of the code that I'm showing right now as well. This is from Solidity. So a really cool thing, one of the cool things that was made for Ethereum in general is that you can specify what version of Solidity you are using or you want to use. So you can actually use old version of Solidity right now because everything on the blockchain is permanent. Everything there is able to be accessed at any time. It would be silly for you to not make a way for you to be able to reutilize older functions.
So in terms of like optimizations, when you write a smart contract, does it actually optimize the compiled bytecode at all?
I think so, yeah. I think that's the way that it would operate.
So with the old versions, does it share the same intermediate representation, or is there like a different version for each backend?
I think there would be a different version, man. But like you probably have to check the docs on that.
No, I wonder.
Yeah,
It'd be an interesting type level question about
to see that the actual like how optimized it actually is. That's an interesting question though. A lot of the programming, a lot of the Solidity code that you're seeing right now is from Solidity version 0.5, 0.6. Right now Solidity is it's in 1 point whatever, and a lot of it has changed. Like right now it's a bit crappy, but you have to typecast everything that you do. It's really ugly. But yeah, so just a real world experience over here on real world examples for underflow. Someone's calling me. The person, so over here you just have this Monero Gold. So this is a real world example of like, so there's Bitcoin, Bitcoin Gold, Bitcoin Diamond, and all sort of stuff. Yeah. So there was Monero Gold, and they had a integer, integer underflow vulnerability. And what ended up happening was that Monero Gold was defunct. Why was it defunct? Because this one person obtained more than the supply of Monero Gold. It times quite a few decimal places, because I think the way that they did it was they used two multiplication signs, so they actually put to the power of the decimal rather than like just the actual multiplying by the decimal, which is such like a silly.
That was a very bronze move of them.
Yeah, very bronze move. So there's different ways. I want to go over what Oracle attacks are. So what an Oracle attack is that what an Oracle is, first of all, an Oracle is some middleware that essentially is able to obtain data and convey that data somewhere else. Right? Why are you laughing?
Secure data links from the bottom. There you go. Very nice.
Yeah. Very cool stuff. So secure data links is just one of the Oracle providers. So Alex and I, we work for a company.
Very good Oracle provider.
An excellent one. Yeah. Show me for the boss. But the way that oracles work is that so you can have centralized oracles, and you're literally just calling like an API, for example, and you're providing that data on chain. So if you're creating some sort of smart contract that executes, let's say you're doing like a flight insurance, so your flight is canceled. You can create a smart contract that just calls Google Flights to see if flights is canceled or not, and then bam, done, easy. But then what's the point of like having a blockchain in the first place? Because now you have this distributed system that's great and all protected and all cool. But then that one trigger data, that one trigger event that you actually want to, be trustless, you don't want it to be from a single source, source of truth. Now it's from Google, right? And we know that Google goes down. Like we experienced that a couple of weeks ago.
Google Plus.
Google Plus. Yeah. So there's Oracle attacks in the sense that people are able to overflow a specific Oracle, or they're able to change the value of real-world oracles such that whenever someone calls an oracle, or calls an oracle that connects to a specific API, for example, or an API aggregate, then that API aggregate now is a false data pool. So you have decentralized oracle networks like Chainlink, for example, that try to solve this problem by having a set of nodes that is able to provide truthful data. But right now it's a bit forced. Like in my opinion, I'm pretty sure Chainlink subsidizes a lot of these nodes. That's why they keep operating. But in the future, whenever staking comes out in 2050, should be all good. Right. Gas, right? So I spoke about gas earlier, though, just to sort of re-emphasize what gas is. It's the payments to the miners. So whenever you send a transaction to Ethereum, you go like, oh shit, I have to pay $50 for this, you know?
$5.
$5 for this, like.
$5.
So Rose jokes, yeah, that's right. But like, why do I have to pay this much money? Because it's a mining situation. So people are expending their CPU and GPU resources in order to calculate the block like, you know, to actually mine the block and put the information inside of the block. So it's like a free market, right? So like, you know, the miners set the price that they want, and you know, you can offer a higher price, and if you offer a higher price, your bid will be prioritized. So whenever you make a Uniswap swap, for example, there's what they call fast gas and standard and slow gas. So fast gas is if you want a transaction to take 3 seconds, and then if you're like a little bit stingy like myself, people like, you know, standard gas and wait 5 minutes. Yeah, and hope that your transaction doesn't get cancelled. Yeah.
We live in the Uniswap era.
So the reason why your transaction wouldn't get picked up by a miner is because someone's always overbidding you, right? So it never gets to your transaction, and then there's like a cancel out, like a call out, like, you know, like your transaction never gets executed into that 20-minute time frame, and as a result, just to not overload the system, they just cancel it out. And you have a gas limit as well, so you pretty much, your gas, it keeps on consuming. It's not something that's like, oh, you know, someone takes a bid and I take it. It's something that's continually consuming because it's being processed within the cloud, like the Ethereum network. So if you reach your gas limit, or if your gas runs out, if your transaction runs out of gas, much like a car, it just breaks. Like, you know, you lose that gas. Like, yeah, what's up?
Is it fair to say that it's atomic?
It's atomic.
Is it atomic? The when you spend your gas?
What do you
if it breaks, will it revert everything I've done so far in like the chain of execution?
Yeah. So like it doesn't get passed onto the chain, yes, but you do lose your gas.
Yeah.
Like you don't get your gas back.
Yeah.
So if you skimped out on the gas on Uniswap, you know, you just have to do two transactions.
So you're telling me I'm not going to be stepping on the gas tonight? Now that I'm going to put in.
That's it, man. You won't be stepping on the gas.
Yeah.
Yeah, you're running out of gas. So you run out of gas. If you run out of gas, you don't have sufficient funds to actually be able to operate that transaction. How not to run out of gas is make sure you have enough gas. Like go to ethergasstation.com and literally like ethergasstation.com and see.
Do a bit of helium every time you're like, I'm putting my money in crypto.
Yeah. So there's exception handling as well that you have to take into consideration whenever you create a smart contract. So you know, make sure you don't run out of gas. Make sure that there's a stack limit that you're able to call on. Make sure that you don't whenever you invoke a transaction, it doesn't call a throw, right? So there's lots of inconsistencies and methods that you're able to actually go through, like an exception that might occur in the blockchain or might occur within your smart contract. And there's lots of ways that you're able to prevent it. I think right now you don't have to worry too much, especially if you use one of the later versions of Solidity, because they have some function callbacks that were introduced later on and all that type of stuff. So they were continually improving since the time that I wrote this. So
cool. This
is not too relevant right now. But if you are using an older version, you just have to be careful. Sure, yeah. It's a bit too much. This is just me talking about how there's different ways to execute and actually send money. You can, call a value. You can literally send to the address. You can send the transfer default is the amount of gas sort of sets in. So this is just me going into a bit more in-depth stuff. So there's fallback functions, which are called whenever you have some sort of, like, it's like exception handling, I believe, for fallback functions over here. Mm-hmm. It's called whenever the client sends money using send transfer. So you need a payable modifier to do this. So payable just means that you're able to actually send money to this contract. So if you have a contract and the function is not payable, it means that you actually aren't able to send money to that function. So yeah, so insecure libraries. So one of the big things when it comes to Ethereum and all that stuff, just use safe math. Like
the D in DAO is for dump, and it's red.
Did you see that? Did I go to the DAO slide by mistake? Sure. Yeah, so like whenever you use libraries in Ethereum and all this type of stuff, much like the auditing, the reason why auditing is so big is just because you have to be careful as to not call like a faulty library or a library that's already defunct, because you might just get used to using a library, but then suddenly the library now has some sort of insecurity. And if you're recalling an existing smart contract, you just have to be sure that, like, as part of your like current smart contract, so you're almost like re-invoking that old smart contract. You just have to be careful to know if that smart contract is actually vulnerable or not, like the security policy of that smart contract. So always use safe math. Don't use your own multiplication functions that you create. Yeah, so reentrancy. So that's a big vulnerability. And much like the DAO that I spoke about earlier, the DAO is a distributed autonomous organization, and it's this really cool thing, big thing whenever Ethereum was introduced, where you are gonna have a system that's self-sustaining. So you're gonna have a system that has governance, that has tokens that support the governance, and the users of the system will be able to they're gonna call the shots. They're gonna be like, oh yeah, I want this to be red, and then they're gonna have like electoral process, and if the vote does pass, then bang, that color becomes red. So that's the big idea, and right now that's actually being executed really well. I mean, like really well. Like Yearn Finance is pretty right. Like its stuff is being alright. Then there's Badger DAO, and then there's like lots of these different DAO protocols that
Badger DAO.
Badger DAO. Yeah, lots of these governance protocols, which is that's one of the big run-ups as to why DeFi is so popular right now, because everyone is able to create like a self-sustaining ecosystem. So it's really popular. Like it's pretty much you can create like a Discord and
Cryptocurrency.
like a Discord, like a Discord and a discourse, right? And you can have like votes, and you can create like your own organization, and then everyone you have to like have these tokens, these governance tokens, in order to be able to elect, to have power within the organizations themselves. So it's really cool. So whenever the DAO was first proposed and was first launched in 2016, I believe, is that when it was launched? I think 2017, 2016, everyone was ecstatic. It was great, wow. And then there was a big fatal flaw that happened, and it was the reentrancy, which was a vulnerability that happened, and it crashed. So the price went like this, everyone was hyped, and then
Yeah, and then the guys involved with Ethereum were like, "Yep, time to roll it back. Nobody loses their money."
yeah, and that's classic Ethereum was born, and the regular Ethereum, classic Ethereum being the community is just like, no, we don't want to participate in that fork because this was a hindsight from the developers. So let's just keep it that way because that's how the world is. Sometimes you fuck up. But the ETH devs are just like, nah,
Yeah.
he's alright.
5 years later, we don't have a set up money supply through Ethereum either. So.
Yeah. Another really bad vulnerability that you can go into is just bad randomness. So the way that you execute random numbers, in my opinion, I think you just should use like VRF functions that like Chainlink made, right? They're pretty damn random. Otherwise, you can you shouldn't use stuff like block.coinbase to check or the hash of a specific block within Ethereum, because depending on how you execute those functions, depending on what order of the transaction it is, or like the actual smart contract it is, people will potentially be able to guess or like predict what those random values are, and then it's not random anymore. And if you have some sort of like vulnerability in your system, you're screwed. And that's just because you didn't take the time to use something that's a little bit more random. Yeah.
In the extreme cases with some randomness sources, some of the ideas people came up with were to use things called verifiable delay functions, right? Where you'd have a code that would just like, you'd sort of have like a recursively packed together number, and it just took a long time to just sort of like get
to that number.
Into like a layer. And the idea is that it's just like you can sort of verify it later on. It's just crazy.
Is this like a new?
No, this is a semi-old thing. It's insane. It's like shit.
Yeah.
Yeah, the invalid randomness is a hard problem.
Yeah. So we'll be able to provide these slides online. Really, that after these slides, I just go on and on about stuff like uints and how you can use maps and arrays in Ethereum, and how it's actually really easy. And if you go home right now, you can write the Fibonacci sequence on Remix, which is the Ethereum compiler online. You can download Geth, which is Go Ethereum client, so you can simulate your own blockchain outside of the blockchain. It's really easy. So if you do want to get into smart contract programming, like be my guest. The first resource that I would recommend to anyone, regardless of their level of expertise, just go on the GitHub or just download Mastering Ethereum by Andreas Antonopoulos. Literally just go Mastering Ethereum or Mastering Bitcoin. Very good resource. Otherwise, just go to the Ethereum website and they have like really cool tutorials and like demos that you're actually able to execute. But it's not hard. It's just smart contracts makes it a bit like intimidating. But half of the applications that use smart contracts, they're on like native or like React or yeah. So literally just Web3 JS. Yeah, that's the library that most people use. So it's not hard. But yeah, that's a quick introduction to Ethereum. Very overviewy some of the histories and some of the vulnerabilities that are involved. And yeah, I hope we have more smart contract developers. What's up?
Were there more slides after this?
Yeah, there were more slides.
Oh,
Yeah.
boy.
Yeah. But like, I'm stopping here.
Yeah,
This is where I put a
yeah.
stop, and I'll provide the next ones. You can provide them on the GitHub or something.
Yeah,
Like
yeah,
that. Yeah.
Sounds good.
Does anyone have any questions regarding Ethereum, smart contract developing, resources? What's up?
What's to stop you purposefully mining your own contract so that you don't have to pay gas?
Nothing.
Nothing. You can mine your own contract. But the reason why people mine in the first place is because they're so the mining gas incentive is that you're expending your own electricity bills for like so would you rather spend X amount of time mining and spending X amount of electricity bills, or would you rather pay like a group of other people to do it? So that's sort of like you can mine your own contracts, absolutely. Like there's no one stopping you to do that. But it's just like a time, money, like transaction thing. And if you have one GPU to mine into the Ethereum like blockchain, it's going to be very hard, actually to do that. Hey,
Yeah, earlier you were talking about sort of cross-chain
sure.
transactions. So you're you're taking an ETH and you're wrapping it into. Is that like interoperability in that way or not? Is that?
It is interoperability, but like not really. It's more like you're creating an equivalent exchange. So it's almost like a bridge, right? So imagine you have a bridge. It's if you've ever played like Dark Souls or something like that, you enter like there's this. It's like fog, like, and you're almost like entering someone else's world, right? But like you're not you anymore. You're like a dark spirit, right? Really bad example.
Well, you said equivalent exchange. I thought of Full Metal Alchemist.
Full Metal Alchemist, right?
You said
So it's rather that you are able to. So you have a container that contains your original tokens, and not every token can be wrapped, mind you. Like you can create a token that is wrapped, and you can create W anything like W BTC, W whatever, but then you have something that has to prove the value of that BTC, right? So once again with the Chainlink shilling, but like proof of reserves is something that oracles are able to do. So you're essentially able to reserve. So you're essentially able to send like 10,000 Bitcoin, and it's stored in a escrow, and then you're able to sort of like validate what the equivalent exchange of that Bitcoin to Ethereum. So you're wrapping it on Bitcoin. So the WBTC is not going to have like one-to-one value because they're completely different. Like they're cross-chain interactions, right? So you need some sort of you can trust the person that created WBTC to be like, 1 Bitcoin is whatever price. But then the better way to do it is rely on some sort of like decentralized Oracle network to do it, because like that's more sort of trustworthy in that sense. So it is cross-chain interoperability, but it's only for like token swaps.
Correct.
So it's just like swaps, yeah.
What about atomic swaps?
What about atomic swaps?
Atomic swaps, as opposed to using like an oracle to verify the on the other side.
You can do atomic swaps,
Yeah,
absolutely. Like
yeah.
I'm pretty sure Polkadot and Ethereum have like atomic swap
Oh,
capability,
yeah.
but then that's something that you have to build into the actual source code itself, rather than something that you can sort of like just wrap and go like about your day. Yeah.
So if you pick up a smart contract that you've written in Ethereum
Sure.
and you want to run it on Binance Smart Chain or something like that,
Sure, you're able to do that though.
and is that because it's the ERC component?
No, it's because Binance has a EVM bridge. So like that's something that Binance. So Binance has an EVM bridge, right?
The smart chain just runs on an EVM.
It runs on the EVM. That's
It
right.
probably runs on a fork,
Yeah.
It's like the guy.
So you can't do that in every blockchain, right? But it's funny that you say like a Binance chain, for example, right, or XDAI or like any EVM based chain, because they have the capability of doing that. And the reason why they wanted to do that is not because otherwise no one would use their chain. Or like people would use BNB chain, right? The Binance Smart Chain, but that's just only if they're like particularly either they're in China because that's their market. Either they use Binance a lot and they want a lot of the rewards. Like, some people that I know working for Algorand, why would you use Algorand, right? Yeah. But like a lot of these chains that do support EVM, they have this cross-chain interoperability. Yeah. In the future, it is something that's going to be like a lot more seamless rather than you having to have EVM interoperability baked into the source code. Like it is going to be something like using some sort of layer 2 solution. I'm not sure about Optimistic, maybe Arbitrum, and you're able to, you have some sort of node that processes in blockchain A, some sort of node that processes in blockchain B. They both use Arbitrum because Arbitrum is blockchain agnostic, and then the off-chain transaction, occurs off-chain, and then all the data can be sent to whatever blockchain actually supports the what's Arbitrum interaction, like layer 2, yeah. But that's like a layer 2 transaction. Like this is like us fantasizing in the future. Hopefully they build it, yeah.
So how do oracles work? How does a contract that lives on the EVM retrieve outside information?
Sure. So how do oracles work? So right now the only oracle, much Alex knows about like to do things one way. The only oracle that I know how it works is just like Chainlink oracles, but they all work in the same way. An oracle is just a middleware piece that gets data, like off-chain data, and then inputs that into like a blockchain, for example.
Okay, so
right?
it's updating state on like other contracts that are on the blockchain, that sort of thing.
Yeah, but the issue, right, with just relying on a specific oracle, right, like just one single source of API, like for example, because multiple blocks need to be confirmed by multiple miners, right? Let's just say that on your contract you have like an API call to Google Weather or whatever it is, right? And you call it at 1 p.m. and 1 second, but then there's lots of miners that call it at the same time, but then there's like a miner that calls it at 1 p.m. and 2 seconds, right? Now you have, and then keep, ad infinite, like infinitely goes on, right? So you aren't able to verify that original transaction, and as a result, you aren't able to put it on the blockchain, right? So then there's the issue. So then comes networks of Oracle, like Band, Chainlink, and a couple of others, which are trying to essentially do the solution for that, where they're able to have this little group, like a little fellowship of nodes that are able to agree upon certain things. They aggregate the data, and then people are able to call that aggregate price of the data, for example, right? Mm-hmm. And some people love to use that because it's very simple, but some people go like, I don't want to use that because that's also a single risk of failure because it's being supported by, the big fat VCs that support the project. So there is like pros and cons of using different Oracle solutions, but all in Oracle is literally just a middleware that connects off-chain data on-chain. And the reason why, as I said, blockchains aren't able to call those APIs in the first place is because whenever you call one API at one specific point, it will not be the same as calling an API at a different specific point. So then you aren't able to confirm the transactions in a decentralized way, in a distributed way. Yeah. Any more questions, guys? If not, Alex will send out a little email with the bunch of deprecated code on the bottom. And thanks for listening. Thank you.
Thanks, everybody. You know what? Before we get back to eating pizza and drinking beer and talking, thank you so much, Adam, for providing this space. We really appreciate it. Thank you. It's a beautiful office.
Wait. And
I didn't mean that randomness quite literally.
And before finalizing.
Yeah.
Before finalizing, please.
What a beautiful photo.
Before finalizing.
Yeah.
I want to put this here in the background, so that no one's able. No, not that one. So that no one's able to forget.
Yeah.
Please check out.
Good thinking.
Mr. Iomete Labs. Not that one, but whenever it loads, go to Iomete Labs.
Yeah.
Blog iometelabs.io.
Please check it out.
Alex and Eric, which is one of Alex's friends, spent quite a lot of time writing a very nice blog post.
It's, yeah, blog post because the site is scuffed. All right, I'll acknowledge that. But you know what?
Yeah.
Yeah.
Oh, look at the comments. Oh my God.
We're getting comments.
Yeah, we're famous already. How many subscribers?
Alex. Nick, no, I'm not gonna say that. Oh Jesus!
I can't believe.
No, dude. Oh.
Alright.
All right.
Don't delete this, please.
Huh? Oh my God.
I can't
Alex, shut up. Thank you, Ben.
I can't believe they did it.
Oh my God. Thank you, Ben.
Thanks, Webby. All right. Can't believe they did it, boys.
Yeah.
Can't believe they.
I guess we should end the stream. Huh?
Yeah.
Okay. Jesus.